Introduction to Computers, June 2005. Copyright 2005 by Dr. R.I. Feigenblatt. Copyright clearances pending. Please don't copy. This is a 100-minute introduction to computers for people who have successfully completed middle or junior high school. It includes important spoken remarks to which you can listen by having the librarian lend you headphones. But you can cover the material in less time by skipping faster between the pages. You don't have to wait for the spoken remarks to complete. To navigate between the pages shown in this presentation, you need only use one or two keys on the keyboard in front of you, the Tab key and the space bar. The Tab key highlights a portion of the screen, like a button, and the space bar will push that button. If you know how to use a computer mouse, it will work as well, but it is not required. There are 5 buttons at the top of the screen you can use. The button labeled First moves you back to this page from anywhere. The button labeled Previous moves you back 1 page. The button labeled Replay reruns the audio on the current page. The button labeled Next moves you forward 1 page. The button labeled Quit will help you close this lesson. Make sure the next button is highlighted. Then hit the space bar now to advance to the next page. Let's start with a definition. What is a computer? People have often talked about the computer as an electronic brain. But an isolated brain is of no use to itself or anyone else. That's why a typical computer is designed to be like a whole animal head, not just the brain. The brain only memorizes and recalls things and thinks, but with the rest of the head, it can also perceive the outside world via its senses and send word into the outside world by making facial expressions. The 4 critical parts of all computers. The table below shows the correspondence between the parts of an animal head and the parts of a computer. In the animal head, we have sensors, the ears, and so on, whereas in the computer, we call the corresponding machinery input devices. The animal head has expressors like its facial muscles. The computer talks about output devices. There's also a brain in the animal head, and it has 2 aspects. Brain memory in the animal head corresponds to memory or storage devices in the computer. Finally, brain thinking in the animal head is like the processing device or devices in the computer. Machines that are not computers. Not all machines or systems that deal with information are computers, because many are comprised of a subset of the 4 critical parts we have identified all computers possess. But they may be parts of computers. 2 examples follow. First, we see a television system consisting of an input device, the camera, and an output device, the receiver. But a television system is not a computer because it lacks both storage and processing. In the second example, we look at sound recordings on vinyl platters. We have 3 parts to this system: a record recorder, the input device, a record which stores the data, and a record player, which is the output device. But likewise, this is not a computer because it lacks processing. Human things that are like computers. The work done by an old-fashioned office staffed by people is very much like the work of a computer. We can identify input, output, memory, and processing aspects in both. In this example, we look at the system built around a tax preparation company. In the middle, you see the office staffed with clerks, which does the processing. As input, it takes W-2 and 1099 forms from its clients. Each time another client comes, it gets a different set of inputs. To process the inputs, The processor or the clerks in the office refer to the memory shown at the bottom. These consist of the tax laws, which are a read-only memory. The processor does not modify them, simply reads them, as well as the worksheet on which the arithmetic of processing is done. It is a read and write memory because the processors, that is to say the clerks, both read and write from the worksheet. Finally, we get the output for each client, the Form 1040. Note that while the inputs and the outputs vary from client to client, the memories are substantially the same. Certainly the read-only memory is the same. That's really what distinguishes what we call memories from what we call input and output. Computers, robots, and animals. A robot is a type of computer whose output devices do significant physical work, rather than act as puny indicators. If a typical computer is like an animal head, then a robot is more like an entire animal. According to this definition, a robot doesn't necessarily have to look like a person or even move around. Your washing machine is one robot you know very well. Another example is a forced air heating system controlled by a thermostat. Animal-like and humanoid robots really exist too. On this page, we see 5 examples. First, we see a very old example, that of an animated town clock in the upper left-hand corner, dating from the early Renaissance. Then we see 4 more robots of recent vintage. At the top right is Sony's iBow, a dog-like creature which is an entertainment robot. It has some amazing properties, including the ability to recognize things by vision or by understanding words that you speak. It moves around and loves to chase its little red ball. At the bottom, you see 3 examples of what people maybe conventionally think of from science fiction films as a robot, something that is in the crude shape of a person. These examples are Honda's Asimo, a trumpet-playing robot from Toyota, and another robot from Fujitsu. A fascinating new type of computer has emerged in recent decades, the neural network. As its name suggests, it takes for its inspiration the nervous systems of living beings rather than machinery. The resemblance to life is far deeper than superficial mimicry of shapes or even nominal function, as in the examples illustrated on this page. Neural network machines are capable of learning by receiving correction from people to trials which test their ability to respond appropriately. In this way, they partially design themselves via adaptation. Neural networks can also be more robust and practical than conventional computers. They are far less prone to serious error if parts of their memory are damaged. And they can often find reasonably good solutions to problems quickly, rather than the best solution after a much longer time, as is typical of more traditional computer designs. Some of the inventions paving the way to the computer. Computers did not come into existence out of the blue all of a sudden. For millennia, people have been concerned with dealing in information and finding ways to make it affect what goes on in the physical world. More particularly, people long labored to devise ways to record and communicate numbers, letters, sounds, and images. They devised multiple ways of doing this using various technologies: mechanical, chemical, electrical, magnetic, and optical. Many of these technologies have fed into what we today call the computer. Some have now been abandoned as obsolete, while others persist to the present day. On this page, we show a dozen of the critical inventions that led to the computers and related systems we know today. Working from top to bottom, column by column, these are: in the first column, the clock, the earliest complicated automatic sequencing machine; the electric telegraph, the first artificial finger and muscle. The teletype, obvious forerunner of today's computer keyboard and printer. In the second column, writing, how we first recorded speech and music for playback later on. The music box, a type of writing in which the sound playback was now automatic. The phonograph, a type of writing in which both sound recording and playback was automated. It was the forerunner to magnetic and optical means of recorded playback, like the secondary memories in computers today. In the third column, movable type, a stamp capable of enormous intricacy, which could be fashioned quickly and easily through the use of modularity. The photochemical camera, which not only recorded all sorts of visual scenes, but would eventually play a key role in making complicated electrical circuits cheap. The integrated circuit, which used optical stamping to do for electrical circuits what movable type did for written matter. Finally, in the fourth column, the telescope, an early artificial display, indeed an optical television set. The Nipkow TV, a mechanical means of scanning images then sent via electricity. The laser, the latest means of transmitting information using electric lights, also a critical component of optical disc memory and laser printers. Now appreciate, computers do more than store and communicate various types of information, like numbers, letters, sounds, and images. They also transform them. This lets us edit such records, as well as make deductions from them, generating new knowledge. We call this type of activity computation because a computer uses numbers to represent all types of information via numerical codes and performs arithmetic operations on these coded numbers to make decisions and generate new information. By means of computation, computers can make contingent decisions and express at least some autonomy. This aspect is what makes computers and robots distinct from simpler types of self-powered electrical and mechanical systems. Both a recorded movie and a video game present us with a moving image we can watch, but they are fundamentally different from one another. You see, a movie is always the same each time you watch it, no matter what you do. But with a video game, what happens depends a very great deal on what you do, because the video game responds to your actions and decides what to do, often in complicated and subtle ways. Because it uses a computer, the video game makes judgments and doesn't simply parrot back a fixed story like a movie. While the video game and the movie both depend on fixed memories to tell a story, the video game also thinks, and so tells a different story each time, depending how we react to the story so far. The key to cheap computers, the integrated circuit or chip. Modern electronic devices are typically built from a small handful of complex closed subassemblies called integrated circuits or chips. The chip owes its existence to the latest stage in the evolution of the mold. The mold is one of the greatest inventions ever. With a mold, a complicated artifact could be designed once, embodied by the mold, and then mass-produced with much less effort. When we started writing on paper, a special type of mold emerged, the stamp. Stamps became especially cheap when Gutenberg realized you could cut them up and recycle the letters in the stamp as well. Early electronic devices like the radio were built by wiring together large separate electronic parts, like resistors, capacitors, and vacuum tubes, all mounted on a board to hold the parts in place. Then someone realized you could forego cutting individual wires to join the parts by printing electrically conductive copper paths on the mounting board itself. We call these printed circuits. But they were not made by pressing a dipped stamp against the board. Instead, a pattern was optically projected onto a copper-covered board, while a chemical bath ate away at the copper according to the pattern, to reveal the circuit paths. So the problem of wiring was largely reduced to that of making a photograph. Finally, it was realized that all the electronic parts the circuit would need could be made from a single shim of pure artificial stone, merely by applying the correct pattern of metals and nonmetals onto its surface. Both the wires and the components could be optically printed. We call this the integrated circuit, or chip for short. Chips allow incredibly complicated circuits with many millions of parts to be duplicated by printing photographs onto shims of rock. Computers would have remained enormously expensive if not for this breakthrough development. Chips are used to make massive computer memories with no moving parts, and they are also used to make the thinking part of a computer, the processor. Because they are so small, computer processors made from a single chip are called microprocessors. The cheapest cost under $1. Many billions are made yearly. But computers began long before chips, or even electricity, were mastered. In the Middle Ages, if not earlier. Let's gain insight into how computers work by looking back to their origin. The clock as computer. If you think about it, the familiar clock qualifies as a computer because it possesses all four aspects we enumerated every computer should include. Let's take the specific example of the mechanical pendulum clock. The clock has two input devices. First, the starting position of the hands can be set by a person, letting the clock know what the current time is. Second, the swinging pendulum lets the clock feel the passage of each second. The clock uses its memory and its sensation of the outside environment as information it will process. After we let go of the hands, they form the clock's memory. It lets the clock remember what the present time is. When the clock feels a tick, it adds 1 second to the time it remembers. If it has accumulated 60 ticks, it resets the seconds to 0 and advances the minutes by 1, doing a carry operation. Very much like when we do a hand addition on paper and carry between columns of Arabic numerals. Of course, the same thing applies to minutes and hours. Finally, the clock expresses the results of its computation via its hands. Above is a summary showing how the clock is a type of computer. Early clock-like computer. You should not be surprised to learn that the first artificial arithmetic calculators of the 17th century used mechanical systems very much like that in a clock. In fact, one such machine, built by Schickard, bore the name calculating clock. Another machine, built by Pascal, even looked a great deal like a clock. Here is a photograph of it, the Pascaline. You may object that while the Pascaline had dials just like a clock, they are not concentric. This is a trivial difference, and in fact, many older timekeeping clocks used non-concentric dials too. Functionally similar to clocks, the gears of the Pascaline behind each dial contain a single offset cog to do carry and borrow operations when they make a complete rotation, so that one can add and subtract. To do arithmetic, one uses a stylus to dial in numerals, just like on an old-time dial telephone. To add, one dials clockwise, and to subtract, one dials the subtractor counterclockwise. Devices like the Pascaline were still widely sold as late as the 1960s. I had a plastic one as a boy. Maybe you did too. And the mechanical adding machines and mechanical cash registers, then in serious use, were descendants of this simple machine also. One more thing. Note that a clock can only display one time at any given moment, just like a cash register can only store one total at any given moment. But we can always hang multiple stop clocks on a wall to remember many times, or many other numbers as we choose, one for each clock. Just like one can add more pages to a loose-leaf notebook to record and so memorize more words one writes with a pen, one can add more machinery to a mechanical memory to record more numbers as well. When we talk of the size of a mechanical memory, we rarely mean the physical size, but rather the quantity of separate numbers it can store and recall. Algorithms and programs. A modern computer can do things which are much more complicated and involved than adding and subtracting numbers. But like the pendulum clock or the Pascaline, it does its work by carrying out a series of steps. Mathematicians have a fancy word for a procedure with a series of complicated steps. They call it an algorithm. It has nothing to do with whether Mr. Al Gore has any rhythm or not. It's just a name. Computers can be taught to do almost any algorithm. We call the description of an algorithm a computer carries out a program. A programmer is a person who takes a human need which a computer can satisfy and devises or adapts an algorithm which will do the job. Then she codes the algorithm as a program which the computer follows to carry out the actual work. You might think of a programmer as a computer manager or computer teacher. The computer is an ideal student because it learns immediately and never forgets. But the computer is very demanding too. Its lessons must be without a single small error. They must also be put into simple language and be unambiguous, with only a single meaning. Today, programmers most often build on the work of other programmers they never met. They depend on the described behavior of programs the latter have written in the past. This can avoid a lot of duplication of effort, but it only works to the extent such trust is well placed. In recent years, many programmers feel this type of dependency is reaching its limits, and they often demand to see the detailed internal design of the program written by others they use too. An algorithm you know, long division. You yourself already know several different algorithms. Two of these are alphabetizing a list of names and doing long division. Every algorithm consists of doing a series of steps, after which the problem is solved. Algorithms have repetitive parts, but in general they also involve deciding when to stop doing one thing and start doing another. They change over when certain conditions are met. For example, in doing long division, when you have guessed the right dividend digit so that your trial subtraction is positive but less than the divisor, you move on to the next numerical column. Else you try yet another guess for the same column. The ability to adapt this way by taking conditional actions is what gives machines that carry out algorithms, computers, their intelligence. Programming the hard way. Rebuild the machine. We saw how we could use a clockwork mechanism to build a machine which can add or subtract. We might take it apart and build another clockwork mechanism that could figure averages. In the old days, people made electrical computers carry out different algorithms by rewiring them. Here is a photo of some women doing just that with a vacuum tube computer called the ENIAC. It was used in World War II to compute artillery firing cables. Note the rewiring plug boards. Machines like the ENIAC used electrical registers to record the temporary results of the calculations it carried out. Because the ENIAC could both read and write these registers, we say they constituted a read-write memory. But its wired plug boards, which embodied the program it ran at any given time, could only be read by the ENIAC, so we say it was a read-only memory. In the ENIAC, memory was used to hold both data and programs, but the memories were of entirely different characters. Programming the easy way. Just enter numbers. A great breakthrough came when Dr. von Neumann realized the computer could be made to rewire itself just by entering different numbers into the read-write memory previously used only to hold the temporary results of calculations. That could be done in a snap. That is what a computer program is today. A sequence of numbers that, when entered into the computer, tells it how to rewire itself so that it can carry out a different algorithm. Put in and activate one program, and the computer can alphabetize a list of names. Put in and activate another program, and it can do long division, and so on. The ability to reprogram the computer so quickly, simply by putting in different information without rebuilding any of it by hand, is what makes it so versatile, something of an anything machine. This flexibility of the hardware led us to introduce a new term, software. Hardware consists of all the physical parts of the computer you can touch, but software is a synonym or alternate name for its programs. Like love, truth, or justice, they are wispy abstractions which can indeed animate the world, but cannot be held in your hand. Some people like to make an analogy with conventional religious ideas. The hardware is the mortal body of the computer, but the software is its spirit, as indestructible as the number 7 or the geometric circle. You can scratch out every last symbol people put down to represent the idea of the quantity 7, but you cannot destroy the idea itself. Sometimes you hear people use the term general-purpose computer. This is a computer which can run almost any program. Distinct from these are special-purpose computers, which always run the same program. Actually, today most of the microprocessors made in the world are used to build special-purpose computers. Say, like the one that runs a satellite TV decoder box. On the other hand, the personal computer, or PC, is a general-purpose computer. Run one program, and it acts like a fancy typewriter. Run another, and it can entertain you with a video game. Run a third, and it simulates a musical instrument. Run a fourth, and it watches your house with a video camera and calls the police when it sees a locked door open. Recorded input-output is renamed secondary memory. Von Neumann's idea was very radical in that it said computer programs were basically just another type of information, and so might be stored, transmitted, or even altered in any way we might manipulate the data we process to perform actual jobs. In his day, computer-compatible input and output devices were few and simple. An example was a teletype machine, an electrical typewriter used before electronic computers to communicate over large distances to another teletypewriter. A single teletypewriter could be used with a computer to do both input and output. Its keyboard could send numbers into the computer's memory, and its printer could receive and present numbers from the computer's memory. After von Neumann, these numbers could either be job data or computer programs. In the diagram above on the left, we see a teletypewriter communicating with a processor shown to its immediate right. The processor also communicates with its electronic memory, shown below it. The teletypewriter could even record and play back its activity, like a financial ticker tape machine or a player piano, by means of a perforated paper tape, which could be automatically punched and later automatically measured for the presence of these holes. In this way, input and output might be either live or recorded. Of course, the use of such external recording media blurred the distinction between computer input-output devices and computer memory. Paper tapes and cards were eventually supplanted by electromagnetic recording media in the shape of tapes, drums, and platters. And rather than try to distinguish between memory and input-output, we introduced new terminology. The old electronic memory of the computer was renamed primary memory. The external recorded media was renamed secondary memory. This is shown in the middle diagram above. The teletypewriter is stripped of its paper tape unit, and a magnetic tape unit is added in its place. Finally, it became common to permanently incorporate secondary memory within the computer itself. Today, if secondary memory can actually be extracted from and replaced in the computer without turning screws, we call it removable secondary memory. We now tend to reserve the naming category of input-output device to that machinery which either observes or produces live activity. Examples are microphones, loudspeakers, cameras, displays, and two-way telecommunications with distant computers connected via networks like the Internet. This is shown in the diagram above on the right. The external magnetic tape unit is replaced by an internal magnetic disk unit, and the teletypewriter is replaced by a video display terminal. As we move toward a more electronic world, we find fewer types of information begin on keyboards and end up on paper. Instead, they move between the primary and secondary memories of large networks of computers. Computers are deterministic. The output a computer renders depends only on the initial state of its memory and the input it receives. There is no randomness to its behavior. It is deterministic. This should be no more surprising than the fact that a pendulum clock set to 4:30 always reads 4:32:17 after 137 swings of the pendulum. A clock that does not is broken. Of course, a few computers actually include a part to create true randomness, but this is rare. Computer hardware is the most reliable thing people have ever built. But most mass-market computer software is the least reliable thing people have ever regularly tolerated. For example, Microsoft estimates major PC application software includes about one error for every 3,000 lines of code or sentences in a program. Software developed for medical, aerospace, and defense applications is enormously more reliable, and costly too. The reliability of computers with high-quality software allows them to run for months or even years without repair, but most people turn PCs off at the end of the day. Computer memories and reliability. Let's look more closely at memory to understand how it impacts upon the reliability of a computer system. PCs include both volatile and persistent types of memories. That is, some memory is erased when power goes off and some is not. The small, fast primary memory used intensively by the processing unit is volatile. It holds both the data we work on doing computation as well as a copy of the program whose algorithm we follow to do that. Primary memory is very much like a working surface in a workshop that is brushed clean of all leftover materials at the end of the workday. But secondary memory is persistent against the removal of power from the PC. It is used to hold both work data and a collection of programs, which the processor can draw into primary memory to start running. Secondary memory is very much like the tools and partially completed work put up on shelves in a workshop. They will be there when the shop opens the next day. Secondary memory typically uses a so-called hard disk made of spinning magnetic platters. Together with the BIOS memory, which is also persistent, these memories and nothing else determine how the computer will respond to inputs coming from the keyboard, the internet, and any external influence when the machine is powered up again. But just because the hard disk and BIOS are persistent does not mean they cannot be rewritten. After all, the former is used to record user data as well as programs. And sometimes we want to change the programs recorded on the hard disk and in the BIOS as well. Unfortunately, ill-behaved software can cause memory to become corrupted over time. The remedy is to restore memory to a known proper configuration. That's why restarting your PC will sometimes solve problems. The accumulated contents of the primary memory will get a fresh start. That's also why good practice includes keeping a backup image for the program stored on your hard disk, and one for the data too. One way to prevent corruption of the programs persistently stored on a PC is to use read-only memory in place of a rewritable hard disk to store them. Examples include optical disks and flash memory with a mechanical switch. Computers, typically synchronous. While computers today use very fast micro-miniature electronics and not the slow, clumsy gears of a mechanical clock, they actually also use an electronic clock to sequence the steps of the algorithms they carry out. If every rower in a galley ship used his oar as he saw fit, oars would constantly bump into one another, and little work would get done. By adding a drummer to call out the cadence, each rower can operate his own oar at the same time and avoid any oar collisions. Likewise, the ticks of the electronic clock in most of today's computers tell the millions of parts in the computer when to carry out the next step of the algorithm. By acting synchronously in this way, they can work in a reliable manner. A human lifetime in 1 second? Today's personal computers, or PCs, have clocks which will tick billions of times per second. In a single second, they advance about as many times as a clock will tick, or a heartbeat, in an entire human lifetime. You can best see evidence of the enormous potential speed of your computer when playing a video game. Everything on the screen is drawn from scratch, 60 or more times per second, from simple stored models. But the speed of its clock, which tells the processing unit how fast to move, may not be the speed bottleneck of the overall PC in other circumstances. Why is my PC so slow? PCs today typically run several programs simultaneously by time-sharing the machinery. The primary memory of the computer is basically as fast as a processor, but it is quite finite in size. If you run too many programs at once, the computer may run out of space. Rather than just stop working, it tries to cope by pretending that space in the very much slower secondary memory is part of primary memory too. Programs with errors, which orphan space in primary memory, mean the longer the PC stays on, the readier this problem can occur. Primary memory is cheap. Make sure you buy plenty to keep this problem at bay, and then reduce the number of programs you run at the same time if you suspect this problem. A program which has to write a lot of data to, or read a lot of data from, a hard disk will be throttled by its very limited speed. And memory issues are not the only reason your computer may seem slow. The bottleneck to your work speed can be a slow scanner, internet connection, or other slow input-output device too. The extravagant practices of programmers can also get you into trouble. As computing power and memory have gotten cheap, they have cared ever less about using them wisely. That's why older software may even be better than newer software. Gratuitous eye candy is one aspect of modern extravagance. If your PC seems too slow, try turning it off if given the option. A senseless waste of your time also follows from software which does not let you immediately abort an activity in progress. Much Microsoft Windows software, even Windows itself, has this problem. Try to find alternatives. A computer connected to the internet, especially a fast so-called broadband connection, is liable to invasion by other computers on the internet. Even with a slow connection, your PC may be probed 500 times per day. Such probes may be motivated by a desire to exploit a known design flaw in your installed software to implant a so-called Trojan horse program, which will harness the computing power of your machine. Some better security practices. But the worst thing about Trojan horses is not loss of computer speed. Indeed, smart ones will not hint at their presence by exposing a noticeable clue like that. The worst thing is that the privacy of your data is lost, and your PC may be put to any nefarious purpose by an unknown party. To avoid such problems, do not install any software from a person, website, firm, or other organization you do not trust with complete control of your computer. And it is not enough to trust the moral character of your source. You must also trust the wisdom of your source, not to be unknowingly subverted. Use a firewall to alert you about otherwise unseen programs which try to communicate via the internet. Patch known security flaws soon, and always keep a patched backup image handy in the event you suspect your PC has been compromised. Sadly, patches for design flaws are not always applied by computer users. One reason is that patches can sometimes break other critical programs on which the user depends. The internet is the primary method by which malicious software, or malware, finds its way into PCs today. PCs are now so very cheap, one possible coping strategy is to get a second PC with minimal information on it, which alone is attached to the internet. You can also use a read-only memory like an optical disc in place of a magnetic disc to store the programs on your internet-attached PC. This will assure that it is not pre-hijacked when it is turned on, at least until a probe can exploit an unpatched design flaw. Everything is just a number. The computer. You may wonder how the computer treats everything as numbers. Sure, things expressed with numerals are obviously numbers, but what about alphabetic letters, sounds, and images? How could they be numbers too? First, let's be precise in our use of language. Our system of numbering notation uses 10 numerals, namely 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. With only these 10 numerals, we can write down any number by using a combination of numerals in multiple columns or places. In what follows, it is important you don't confuse two different words, numeral and number. For example, 2005 is a number written with 3 different numerals, 0, 2, and 5. Sorting and searching by the numbers. Searching for something is much easier when it is among things which have been sorted earlier. For centuries, sorting and searching have been very important activities in an office based on paper records. They are also among the most vital things we use computers to do. Let's consider words made up of alphabetic letters and see how the words can be like numbers. Sorting numbers versus sorting names. Think about what you do when you sort a list of names alphabetically. You know that the letter F comes after the letter E, but before the letter G. Just like you know the numeral 6 comes after the numeral 5, but before the numeral 7. And just like you sort a list of numbers by looking at the columns one at a time, starting at the left and working right, you do the same with letters in a name. You start sorting by the letter at the leftmost position in the names and working right too. So in alphabetizing a list of names, you treat the names like numbers, and so put the smaller names first, although we say alphabetically earlier names rather than smaller names. Listing and sorting things using multiple denominations. Let's look at it a different way. Consider sorting a list of clock times into order. We can write down a single time by writing down the hours, then the minutes, then the seconds in 3 sequential columns. To put a list of times in order, first we sort the times by the hours column, which can vary from 0 to 23 in a 24-hour clock scheme. Then we sort the times with the same hours by minutes, which can vary from 0 to 59. Finally, we sort the times with the same hours and the same minutes by seconds, which again vary from 0 to 59. Now let's go back to sorting a list of names instead. If we were to replace each letter in a name by a number which shows the order that letter occurs in the alphabet, starting with 0, we get something that looks vaguely like clock times. But with a name, each column could vary from 0 to 25. There are 26 letters. While we saw that columns in clock times vary either from 0 to 23 or from 0 to 59. So you see, the letters in the name can be treated like 26 distinct numerals. In fact, if our pair of hands had 26 fingers instead of 10 fingers, our numbering system would probably use 26 numerals rather than the 10 we do. Quantity of fingers inspires the choice of number base. If we had 13 fingers on each hand, for a total of 26 on a pair of hands, we would probably use a numbering system with 26 numerals. Our addition table would be bigger too. Instead of having 10 times 10 equal 100 entries, it would have 26 times 26 equals 676 entries, and so on. But we would be just as capable of doing arithmetic with a system using 26 numerals as we do using one which uses only 10. But surely the much bigger addition table would take much longer to learn. Mathematicians have a name for the quantity of numerals a numbering notation system uses. They call it the base. With our 10 human numerals, our system is called base 10. Sometimes we call it the decimal system, because deci is the Latin prefix meaning 10. You probably have heard of the Dewey Decimal System for putting books in order. That is a good name because it uses our conventional numbering notation with 10 numerals. But if we had 26 fingers on our 2 hands, we'd probably use a notation system for numbers which had 26 numerals. Maybe we'd even have the alphabet do double duty, both as letters and the 26 numerals of such a base 26 system. Base 10 decimal addition table. It may interest you to know that the cheapest way to build a computer is not to have it use base 10, much less base 26. Virtually all computers today use base 2 internally and convert between base 2 and base 10 when communicating numbers with people. Base 2 is the smallest base that can be used to make multiple columns of numerals represent large numbers efficiently. And just think, if the base 10 number system has 10 times 10 equal 100 entries in its addition table, as shown on this page, then the base 2 system only has 2 times 2 equals 4. That makes teaching a computer how to add very simple. Base 2 binary addition table. The simplicity of performing mathematical operations is why we build computers to use base 2, also called binary. Computers only need 2 numerals, 0 and 1. With just those 2 numerals, the computer can record numbers of any size by using enough numeral places, just like we people can express very large numbers by using enough numeral places with our 10 numeral system. but computers need about triple as many numeral places as we people do to represent a given number. Observe that anything with two possible alternatives can be used to record a binary numeral. For example, a coin, which is either heads or tails up, or, as another example, a simple electrical toggle switch, which is open or closed, or, as a third example, shown in the photograph here, a microscopic ridge on the surface of a CD, which is either present or absent, among many other examples. 8 binary numeral places, or bits, to a byte. Today, it is very common practice to group binary numeral places, also called bits, 8 at a time, and call the collection a byte. Because 8 2's multiplied together are 2 times 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 2 equals 256, a single byte can represent any number between 0 and 255, which is one less than 256. You will hear the size of computer memories measured in bytes. Of course, a memory with a certain number of bytes can record exactly 8 times as many binary numerals, or bits, because there are 8 bits per byte. Bytes are a handy size because they can be used to record one of a choice of up to 256 arbitrary alternative symbols. For example, a byte can store a number which represents one of our 10 decimal numerals, or one of our 26 uppercase alphabetic letters, or one of our 26 lowercase letters, as well as leaving 256 minus 10 minus 26 minus 26 equals 194 other numerical code values to represent things like punctuation marks. Cutting up images, digital quilting. Now perhaps you accept that computers can treat alphabetic words like numbers, but you may still wonder how the computer can treat sounds and images like numbers too. Let's start with images. Imagine printing an image as a photograph. Then slice the photo up without disturbing the pieces, so that the cuts look like the equally spaced rows and columns of a checkerboard. A checkerboard only has 8 rows and 8 columns, for a total of 8 times 8 equals 64 squares. But what if we cut the photograph up much finer, making many more equal-sized squares? Eventually, the squares would be so small, the brightness and color of each square would be uniform. We could measure the brightness of each square with a light meter and record the number the meter showed. If we did that for each square and recorded all the numbers in a table with rows and columns which mimic the relative positions of all the squares in the photo, we would have a way of representing an image with a collection of numbers. This is exactly what computers do when they look at the world with electronic cameras or scanners. The computer can also turn a table of numbers into an image by using the numbers to set the individual intensities of a massive collection of equally spaced microscopic electrical lamps organized into rows and columns. This is exactly what it does to draw on a display screen, similar to a TV set. Television using whole rows to multiplex. The optical telescope is a type of television invented shortly after the Middle Ages. But the magnification one can achieve is rather finite, limiting its range. And the curvature of the Earth introduces additional problems. But an image we might send with an electrical wire can span the globe. The first workable electrical television scheme was described in the late 19th century, even though we don't know of a working model built until much later. Still, The method used to chop up an image into constant intensity segments, which are then reassembled in the same order at the other end, worked exactly the same way today's computer turns images into numbers and numbers back into images. In the late 19th century, the expensive way to do this would have used a separate light meter for each square of the source image and a separate light bulb on the other end, which is what we do in the 21st century. This involves thousands or even millions of light meters and light bulbs, and it would seem as many wires connecting each pair of meter and bulb. Imagine that, a cable running from TV studio many miles to a TV receiver with millions of wires in it. Does that sound practical? Instead, a clever 19th century person named Nipkow realized you could do TV using a single light meter, a single wire, and a single light bulb. His scheme used a special optical shutter in the form of a largely solid wheel spinning between the source image and the light meter, as shown in the diagram. Note the wheel was not entirely solid. It had a series of small holes in it used as peepholes, and each hole was a different distance from the center of rotation. At any given instant, only one of the holes allowed the light meter to peek through the wheel and see part of the image. And as the wheel turned, which part of the image the hole let the meter look at changed too, sweeping a peep line across the source image field. As hole after hole swept viewing lines over different portions of the image, eventually every portion of the image would have its light intensity measured in turn. And after the wheel made a full rotation, a whole new series of identical measurements would be made, allowing changes in a moving image to be observed. The single meter in this electrical camera would generate a varying electrical signal, which could be fed into a wire to operate a receiver far away. At the receiver end, the image would be reassembled in lockstep with the camera. It would use a single light bulb powered by the wire from the camera. But the light bulb would be shuttered by a spinning wheel identical to that used at the camera end, spinning exactly as fast. The whole system would look as shown above. Today, we no longer use mechanical systems to slice up and reassemble the portions of an image to make a television system. We have more sophisticated, yet affordable methods. But we still avoid using more than a single wire to send the signal when we desire, by sending the light intensities of image portions in a known spatial sequence. We call this multiplexing. Realize that when a computer uses both an electronic camera and an electronic display, it is as if it has taken a whole TV system and stuck itself in between the studio and the receiver. It could simply pass along signals from the camera to the display, in which case we would have simple live TV again. But it could also manipulate the camera images by doing arithmetic on the numbers used to represent those images before it sends the results to the display. And it could even store the numbers of incoming images in its memory and not bother sending them to the display at all for now. And later on, it could send them to the display in any order at all, at any speed, by recalling the numbers it stored in its memory earlier, with or without any modifications. Sound can be represented with numbers in a similar way we use to represent images. But rather than a series of tables to represent a series of images, sound requires just a simple list of single measurements. Sound is just the variation of air pressure. Just like we use a pressure meter to measure the water pressure in a boiler, we could use a pressure meter to measure the pressure of the air. If we made regular measurements of the air pressure frequently enough, the pressure would not change much between measurements, and we could track the variation in air pressure, which is sound, very faithfully. By recording these numbers in a list, we would have a numerical representation of the sound. This is exactly what a computer does when it listens to the world with an electrical air pressure meter called a microphone. The computer can also turn a list of numbers into a sound. It uses those numbers to control how hard it sequentially pulls on the diaphragm of a loudspeaker, and out comes sound. Thus, anything that can be measured with an electrical meter can be turned into a set of numbers, and so can be dealt with by a computer. Good place to take a break. If you've listened to all the spoken remarks, the lesson so far has taken about 50 minutes. We have now completed our short study of how computers work. Coming up is an optional 10-minute review of graphing. It is followed by a 40-minute section which quantifies the progress computers have made, as well as how they have affected the world in which we live over the last few decades. Business people and community leaders will likely find this section of great interest. Detour, tutorial on graphing trends. Soon, we will describe the amazing progress computers have made in recent decades. If you are comfortable understanding how to use graphs to illustrate trends over time, you can skip ahead until you see a page labeled Amazing Progress. If not, we will now spend a little time explaining how graphs work. Let's consider how we might try to see if summers are getting hotter over time. For example, we might try to record the high temperature on the first day of summer every year and write them down in a table. To measure the temperature, we might use the same mercury thermometer each year, which we show here recording 75 degrees in 2001. We could then write down the temperature in a table, such as we show on this page. With a very few numbers, as in the present example of 4 years, it might be easy to discover any trend. But if we had dozens or hundreds of numbers, it would be very much harder. Luckily, there is a trick we can pull to turn numbers into a picture that is much easier to understand. We will show how this works using a simple example here so that you can follow how it works in detail. Flip to the next page to begin. Detour, tutorial on graphing trends. In place of the table of numbers, we might instead record the history of temperatures by taking a photograph of the thermometer each year and then laying the photographs next to one another in order, so that we know which is which. At the bottom of each photo, we'd label the year it was taken. Some of the advantages of doing things this way are obvious at once. For example, it is very easy for our eye to pick out the year the temperature was highest. We don't have to compare every last number in a table one at a time. We just look at the collection of photos and out pops the year the temperature was highest. We can also see that temperature was falling at about a constant rate between 2002 and 2004. We don't have to do any subtractions with numbers. Our eyes are great at comparing distances with one another at a glance. Of course, with all the details of the real-world thermometer in the photo, paying attention to the tops of the mercury columns is harder than it has to be because of the distractions. For example, the temperature scale is labeled in each photograph. While that helps us line up the photos, after we have done that, it just makes for a lot of clutter. What if we could modify the photographs to reduce the clutter? See how we do that by flipping to the next page. Detour, tutorials on graphing trends. Here we have removed the repetitive numbering and simply extended the temperature tick marks of the first thermometer so that it reaches across all of the thermometers as lines. It is now easier to pay attention to the important thing, where the tops of the mercury columns reach in each thermometer. But maybe we could even do a little better. The bulbs supplying a pool of mercury to each thermometer tend to stand out because of their size. Maybe we could make the tops of the mercury columns stand out the same way by modifying the photos again. Flip to the next page to see how. Detour, tutorial on graphing trends. Adding balls to make the top of the mercury column stand out worked. But the rest of the thermometer bodies still are pretty distracting. They do bestow one benefit, however. They help us label the year each temperature was measured, just like the black horizontal lines help us read off the numerical temperature values. So let's try replacing the thermometer bodies by black vertical lines as well. Flip to the next page to see the results. Detour, tutorial on graphing trends. The final results are what we want. We now have a Cartesian graph. We'll call it a graph for short. Graphs are not just restricted to showing how temperatures vary over time. They can be used to show how one thing changes when we change something else. Perhaps you think the size of the balls tends to block the marking lines. Well, we are free to make them as large or small as we like. In general, they should be large enough to see clearly, but small enough not to block the marking lines. But sometimes we let the size of the balls represent additional useful information, namely how uncertain we are about the correct actual numerical value of the vertical or horizontal offset of the ball. On the next page, we will display the values of other things measured in the 4 years shown to explain why we might like to use a very different set of markings along the vertical scale. Flip to it now. Detour, tutorial on graphing trends. These are not temperatures, but measurements of how much toxic material is dissolved in a river we want to clean up. We want to use a graph to show the progress we are making. Originally, in 2001, there was 100 grams of toxin per swimming pool-sized water sample. A great deal of progress was made the first year, as the most obvious sources of pollution were discovered and eliminated. In later years, the amount of pollution is close to 0 grams per water sample. Does this mean no progress was made after 2001? When numbers vary a great deal in size, we can use a special way of marking a scale to let us examine their variation all at the same time. Flip to the next page to see this way. Detour, tutorial on graphing trends. The horizontal scale is the same as before. It is proportional to the year, or as a mathematician would say, it is linear. But looking at the left, we see the vertical scale is no longer linear. It is logarithmic. Rather than space markings by a constant difference between numbers, we space markings by a constant multiplicative factor. Notice that the space between the 1 and 10 markings is the same as the space between the 10 and 100 markings. That's because both pairs represent the same tenfold change. And observe the advantage of marking things this way. Now the continuing decline in the amount of toxin in the water is very evident. We are continuing to make progress in the fight against pollution, but it becomes harder and harder as we have to seek out ever more subtle sources of contamination. When we combine a logarithmic scale with a linear scale, we call the combination a semi-logarithmic graph. When the linear scale is the time, a straight line indicates the thing we are measuring is changing at a constant rate of change, say like 10% per month. The dots on this graph almost fit on such a line, so we see we are shrinking the pollution in the river at a constant rate. Finally, look at the scale on the right. We have used another method to label how many grams of toxin we find in a water sample. Rather than use numbers with a decimal point, as we do on the scale on the left-hand side, we always write the number 10 with a second, smaller number called an exponent, slightly above and to the right of the 10. The exponent has this meaning. If we were to look at the value written on the corresponding marking on the left-hand side scale, that would be the number of zeros the numeral 1 was found to the left of the decimal point. Notice that when the 1 is actually to the right of the decimal point on the left-hand side scale, the exponent on the right-hand side scale is appropriately negative. If you have understood everything in this detour on graphing trends, you should be able to interpret in detail the graphs we will now present. If not, you can still get a lot out of what we will have to say. But graphing is important, and every educated adult needs to master graphs. Amazing progress. Somewhat over 2 centuries ago, new chemically powered machines, like the steam engine, gave birth to what is called the Industrial Revolution. Material wealth per person rose dramatically, and the worlds of work, commerce, and social life changed in ways no one could imagine. In recent decades, there has been amazing progress in computer technology. Prices have plummeted in a way totally unprecedented for any technology in all of human history. Because of this, there has been a massive uptake of this technology. This is producing change whose speed is putting even the original Industrial Revolution to shame, and it is only just beginning. Moore's Law of Miniaturization. Electronic chip part density doubles every 18 months. The amazing progress in integrated circuits, or chips, since 1970 is revealed by the numbers plotted in this Cartesian graph. The horizontal scale shows the year, and the vertical scale shows several different quantities on logarithmic scales. The blue markings in the graph show the progress in microprocessors. We measure their complexity by counting the number of electronic switches, called transistors, each contained. Around 1970, the first microprocessors only had a few hundred transistors. But only 3 decades later, at the turn of the century, they had dozens of millions of them. Integrated circuits, or chips, can also be used to make the fast primary memory computers use. The red markings show the progress in doing this. Around 1970, a chip could only store about 1,000 binary numerals, or bits. But by the turn of the century, they could store hundreds of millions of them. You might think people got ever more components on a chip by making it bigger and bigger, but you would be basically wrong. What has actually happened was that improvements allowed us to put down patterns on chips in ever finer detail, making components smaller, and so permitting us to increase the number of them which can occupy the same space. Empirically, the number of circuit components per area has grown at about a constant rate, which doubles density every 18 months. We call this trend Moore's Law, after the person who first suggested it. Why is Moore's Law important? Well, the cost of the chip is largely determined by its area, not by the number of components it holds. That means as we squeeze more and more components onto a chip of a given size, they are free. The cost per bit will keep going down and down and down. This is shown by the green markings. Let's put in some specific numbers to see how much costs have fallen. In the 1950s and 1960s, primary memory in computers was not made of chips, but instead used thousands of tiny donut-shaped electromagnets woven into fabrics stretched out on frames. This so-called core memory cost about $1 per bit to build. Primary computer memories were very small. They could only store a little information because storing a bit was so expensive. A 1 megabit memory, which could only store about 1/10 of the text in a typical book, would cost $1 million. Then chip memory started to replace core memory as primary memory. We see that around 1970, a bit of memory could be stored for 10 cents. That would let us replace a $1 million core memory with a chip memory that only cost $100,000. And in the next dozen years, chip memory prices plummeted by a factor of 1,000. By 1982, the $1 million memory now only costs $100. With memory so cheap, businesses could afford more than a single large computer the whole company would share. Offices all over the developed world started giving individual workers millions of personal computers, or PCs. We might guess that the explosion in demand kept supplies constrained, so that even as incremental manufacturing costs plummeted, the cost of building many incredibly expensive high-tech factories to make more chips kept consumers from seeing price drops for a very long time. In the next 15 years, memory prices only dropped another factor of 10, but that still meant the $1 million memory now costs only $10 by 1995, the dawn of the mass-market internet explosion. And then a second period of price collapse emerged. In only the next half-decade, prices dropped by another factor of 1,000. As the 21st century began, the memory which had once cost $1 million would now only set you back a single penny. That's a price improvement of 100 million times in less than half a human lifespan. And that $1 million memory for a penny was about 100 times or more faster as well. The one advantage the old core memory had over the chip memories discussed here is that they were non-volatile. They would not forget if you shut power to them off. This was of advantage in certain circumstances. But it turns out a special type of chip memory called flash memory is non-volatile as well, although it is as slow as the old core memory and can only be rewritten 1 million times before it wears out. Still, flash memory is as cheap as other types of chip memory, and so can be used today to ferry a gigabyte of data with a coin-sized package costing $100. It has enough space to hold the text of 1,000 books. The exponential growth of computing, 1900 through 1998. The amazing increase we saw in the amount of memory a dollar buys is also seen here in improving processing speed over time. This summary was compiled by the famous computer inventor Ray Kurzweil. It shows how fast a processor with a capital cost of $1,000 computes, measured in calculations per second. Between 1970, when the microprocessor era began, and the turn of the century, processing speed is up by a factor just a tad shy of 1 million. But what I also find interesting is that the dramatic increase in processing speed per dollar predates the age of microprocessors. For example, over the second half of the 20th century, it improved by a factor of 100 million times. Recent increases in processing power have allowed us to use brute force to enable computers to understand visual information at once. That's why the Aibo robot dog can chase after its red ball, and yet Sony can now sell this toy for under $1,000. Chip progress is not the only cause of price drops. The magnetic hard disks we now typically use for the secondary memory of PCs has been around for decades, and it has seen amazing and accelerating price decreases too. Unlike microprocessors and primary memories, whose plummeting prices owe thanks to the ever-multiplying miniaturization of electronic components on chips, the falling price of magnetic hard disks derive from the decreasing size of the area on their surface, which can be independently magnetized in one direction or another. So it is by the grace of miniaturization as well. Here we show the capital cost of a portion of magnetic hard disk large enough to store a megabyte of information, roughly equivalent to the amount of text in a book. In 1970, storing a book on disk cost $1,000. Even by the mid-1980s, it still cost $100. But by the early 90s, it had fallen to the $2 or $3 it cost to manufacture a traditional paperback book holding the same information. But the price of magnetic disks continued to plummet rapidly. By 2002, it only cost 1/10 of a penny to store the text of a book on magnetic disk. The price had fallen 1,000,000-fold since 1970. Alphabetic text storage in 2005, a comparison of various media. For centuries, paper has allowed us to reliably store information in a highly compact form for relatively little expense. It is because of paper and related media that we have preserved the words written down by people now millennia dead. We have the Bible today because we had paper long yesterdays ago. But new digital media are emerging to replace our old friend paper. They can store the same information which paper can in far less space, or for far less expense, or both. The data they hold can be copied almost for free, and such data is easily communicated anywhere on Earth at the speed of light over networks. Because computers read millions of times as fast as people do, searching is also incredibly cheap with digital storage. The graphic on this page summarizes two aspects for both traditional and digital storage media: the cost of making the storage and the volumetric density with which alphabetic-based information can be stored. We see that one traditional, if modern storage medium, microfilm, and its sheet-like cousin, the microfiche, greatly reduce the amount of space needed to store information relative to paper, by a factor of about 1,000. But it does not save much on expense. If one uses acid-free paper, paper records can easily last a century, many centuries under the right storage conditions. Microfilm is also stable for at least a century, and perhaps 5 centuries with polyester-based photofilms. Flash memory, a non-volatile type of chip memory, is much more compact way to store alphabetic-based information than is even microfilm. We gain about another factor of 1,000. More importantly, we save on capital cost if the information is in digital form, a factor of dozens. A potential drawback of flash memory is that it is only designed to remember for about a decade. It has to be recopied again and again forever in less time than that to save the information it contains forever. Additionally, there are two subtle problems with the use of digital storage, which paper and microfilm avoid. First, unless the alphabetic information is captured digitally at the time of creation, it is very expensive to digitize this information later, at least for now. It costs about $10 per book to do this, several times what it costs to mass produce a single copy of a paperback book. Second, digital media are constantly evolving, and new machines are required to read new media. This results in old reading machines being abandoned, orphaning data stored in the type of media they were able to read. Use of digital media in an archival setting means that the entire archive has to be recopied every time there is a generational change of equipment. In a related example, the National Archives of the United States keeps 2 copies of its old magnetic tapes and refreshes them every 10 years. Speaking of magnetic media, we see that magnetic hard disks are just as compact as flash memory and 100 times cheaper in the bargain. By now, disks are as cheap as tape, and the latter are being abandoned. Cheaper yet, if not quite as compact, are optical disc media like CDs and DVDs. When these are pressed from a mold, experts believe they will be reliable for about a century. But mastering costs for a mold are almost $1,000, thousands of times the cost of individual optical disc blanks. That means that unless we make numerous copies of an optical disc, we cannot use a mold and still enjoy a price advantage over magnetic media. There are alternative versions of CDs and DVDs which require no mold to be made. They can be exposed photographically like traditional photographic film. We use the term burning to refer to this process. They can be made one at a time. But the jury is out on how long one can rely on them to last. Under the right conditions, some may last a century, like pressed discs, but it is not uncommon for them to fail in a couple years. An archiving regimen using such discs might keep 2 copies of every disc and recopy them each year. The good news is that you could store 5,000 books on a DVD blank that costs 25 cents and can be burned in under an hour. I am not that worried about the stability of storage on optical discs because I feel we will not have to refresh them too many generations before we have new media which are much more reliable for no greater cost. One final note. In this graphic, we assume the information we want to store uses symbols like the alphabet. If we wanted to store complex one-of-a-kind graphics and photographs, we could not store nearly as many books on a disk. Indeed, even the best new digital media would not manifest enormous gains in space and manufacturing costs over that of microfilm-based solutions. Cloudy crystal balls. It's not always easy projecting where technology will go and how long it will take to gain commercial acceptance and what small critical change will be necessary to make that occur. I exemplify that with a couple of quotations here. In 1880, Thomas Edison, inventor of the phonograph, said, "The phonograph is not of any commercial value." And it wasn't for want of trying. He didn't simply invent things for the fun of it. He was trying to make money, but he couldn't make a commercial success of his phonograph. It wasn't until 20 years later, when a variation called the gramophone emerged, that audio recording became a mass market success in the consumer market. The gramophone differed from Edison's phonograph in that in place of a cylinder, it used a platter with a spirally cut groove, the thing we're familiar with in vinyl phonographs of the 20th century. And in addition, rather than using a hand crank mechanism, it used an electric motor so that the speed of the playback was extremely well controlled, and there weren't pitch variations which made the Edison phonograph cylinders unpleasant to listen to. And the other quote comes from the president of the Michigan Savings Bank, supposedly said to Henry Ford's lawyer, "The horse is here to stay, but the automobile is only a novelty, a fad, a passing fancy." Now, how many cars do you see for each horse today? So you see, it's very difficult, even when something's been perfected, to see the entire commercial consequences of its life and how long it will take to become successful. Cloudy crystal balls. Now, predicting the future of computer technology, even by computer executives, was incredibly difficult, in no small part because you see what incredible success, what incredible improvement all the basic technologies have had over the past decades. And so let's take a look at what we were told by the people who should have known long ago. Thomas Watson, chairman of IBM, which eventually became the largest computer manufacturer, said the following in 1943. I think there is an annual world market for about 5 computers. And today, the microprocessor market is hundreds, not hundreds per year, hundreds per second. Then in 1977, Ken Olsen, the president of Digital Equipment Corporation, which was then the largest mini-computer maker, said, there is no reason for any individual to have a computer in their home. And today, the majority of Georgia homes have a PC, and a PC that is, or on short notice, can be connected to the internet. How the U.S. business investment dollar was spent. Businesses have always put some part of their capital budget towards buying information processing equipment. A half-century ago in 1950, that meant things like typewriters, filing cabinets, some telephones, and maybe the occasional rare teletypewriter, but not much else. But in recent decades, the fraction of the business investment dollar devoted to buying capital equipment that's for information processing has exploded. And the reason is that this equipment has become much cheaper and much more capable, so that by 1997, we were also buying things like copying machines, personal computers, cell phones, and a tremendous variety of things we could not imagine back in 1950. And in this chart, you see the quantitative representation of this increase. We show how the capital investment dollar was divided for various types of business equipment, looking at information processing equipment, industrial equipment, transportation equipment, structures, which is to say buildings, as well as other types of equipment. And you see that between 1950 and 1997, the fraction devoted to information processing went from 6 cents on the dollar to 25 cents on the dollar, more than quadrupling. Capital expenditures for information processing equipment now is bigger than for any other category of business equipment except for structures, which it is appearing to close on in any instance. Walmart, major user of computer systems. Walmart presents a very clear example of how intensively information processing is used in a modern, successful business. And the way to try to measure the intensity of something like that might be to look at how much data they keep online at all times and how that compares to other parameters of the business. Walmart reports that they keep 460 terabytes of data online. That's the equivalent of 460 million books of text. Now, they have over 5,000 stores worldwide, but if we were to divide the amount of data they have online by the number of stores in the world, we would find that they keep records of equivalent to about 90,000 books for each store they operate. And if you look at their workforce of 1.2 million workers worldwide, they keep the equivalent of 400 books of information for every associate. About 100 million people per week walk into their stores in the United States, and Walmart keeps about 5 books each for each one of them that walks in during the week. Finally, if you looked at their annual sales of about $285 billion, for every $600 of merchandise they sell in a year, they maintain about 1 book of information in computer systems. So you see, the use is very intense. Massive electronic business-to-business sales. Now, you know, an alternative to going to Walmart to buy something is to use the internet to get something at retail. There are famous firms which do that. For example, Amazon, which started selling books, now sells electronics and a whole variety of things, and eBay, which are like garage sales, or at least they started out that way, and now sell a variety of things on a open marketplace, very much like a worldwide bazaar. But retail buying on the internet is still relatively small compared to the real world in-person buying we do at places like Walmart and Sears and Home Depot. But what people don't realize is that the sales between businesses of merchandise and services mediated by electronic markets is absolutely huge. And let me just read this quote from the May 2003 New York Times. Almost no one foresaw the web's explosive growth, just as few foresaw the dot-com bubble or the death of thousands of startups when it burst. Yet as a recent cover story in Business Week, the eBiz Surprise noted, the projections of the growth in internet commerce made in the bubble days of 1999 have proved pretty accurate. E-commerce between businesses in the United States will reach an estimated $2.4 trillion this year, according to Forrester Research, while e-commerce sales to consumers are projected at $95 billion. To give you an idea of how significant these numbers are, bear in mind that the gross domestic product of the United States is about $10 trillion, and there are about 100 million homes in the country. So one way of putting these numbers into more human terms is that business sales to consumers via e-commerce, that is to say the internet, average about $1,000 per home each year. But sales between businesses via e-commerce are about $2,000 per home per month, not per year. So it's 24 times the size of the business to consumer sales. There's a new book as I record this, which is at or near the top of the bestseller list, written by Thomas L. Friedman, a 3-time Pulitzer Prize winner. The book is called The World is Flat, A Brief History of the 21st Century, and it does an absolutely splendid job of explaining to the intelligent, interested layperson what the fallout from computer and internet technology is on dramatic changes now emerging in the world of commerce and business worldwide. To quote from the Amazon editorial review here, what Friedman means by flat is connected. The lowering of trade and political barriers and the exponential technical advances of the digital revolution have made it possible to do business, or almost anything else, instantaneously with billions of other people across the planet. An interesting example of the trends that Friedman writes about in his book, The World is Flat, comes from the Annenberg CPB channel material for grades 7 through 12 geography instruction. In particular, Teaching Geography Workshop 8, Global Forces, Local Impact. It was written sometime in 2001 or later. And the quote from this cable TV program is, in just the last 15 years, the cost of shipping a VCR across the Pacific was reduced by 95%, from $30 to about $1.50. And this isn't because fuels or ships have gotten any cheaper or sailors work for less. No, by means of automation, enormous efficiency has been wrought in the logistics of crossing the globe. And firms like Atlanta headquartered UPS are leaders in this sort of information, and they're profiled in detail in Friedman's book. No longer just a factory worker. The information technology revolution is changing all sorts of work, including jobs that you might not suspect. I quote here from a report I wrote, commissioned by the Haralson County government about 5 years ago. And what I wrote is this. There is lots of growth in automobile production here in the South. although the qualifications required to participate are becoming ever more demanding. By 1996, the pattern was clear. Quote, "A new industrial revolution has begun. Increasingly, manufacturers value a strong mind instead of a strong back when hiring factory workers, according to new research. Now that they are hiring again, the big three automakers are putting quick minds ahead of strong bodies and putting job applicants through a grueling selection process that emphasizes mental acuity and communication skills." A more recent observation, which is very germane to this, was made by the head of the Haralson County Development Authority, Joan Young, in spring 2005 at the Buchanan Town meeting. And what she said was, "They're full of computers." And that was her description of the Chronospan plants she visited in Europe, in Salzburg and Dresden, in anticipation of possible sighting of a similar plant in Buchanan. While the plant won't be built now, it would have produced simple laminated floor tiles, not rockets to Mars. Information everywhere. The information technology revolution has done more than change commerce. It's also changed a lot of the internal operations of companies. And a quote from Technology Review in July 2003 we have here is illuminating. In 1959, Peter Drucker looked at the emerging work world and coined the term knowledge worker. He anticipated the revolutionary change from an industrial society to an office-based one, where people rely on technology to perform their jobs. Knowledge work is generally considered to be the domain of highly paid scientists and engineers, professionals and managers. A transformation that's perhaps less noticeable, but just as important, is the intensive use of information in jobs of all types, from call center representatives to truck drivers to factory workers. It's become a subset of a much broader occupational category we define as information work. The majority of workers constantly use data, information, and knowledge to various degrees in their jobs. Here's a table that tries to summarize the amazing impact digital technology has made on all sorts of common appliances used in business, personal life, and everywhere in between. Digital devices use computers to perform specialized functions, and often in compact packages. The numbers sold each year are huge and growing, as you can see for yourself. You might be quite surprised at how very long we've dealt with the issue of automation of work, at least in certain sectors of the economy. It turns out that the oldest industrial robot, the Jacquard loom, is over two centuries old. A model is shown here on this page. It was capable of weaving arbitrary patterns by using design instructions recorded in a belt of punch cards. But in all the time since, machines have not put people out of work for good, because people have unique strengths which are then drawn upon to complement the things the machines can do better. As old work is automated, its produce becomes cheap, and the expense spared allows consumers to pay for new services the displaced workforce then fills. And here's a little table emphasizing what people are good at and what machines are good at. Human strengths include judgment, pattern recognition, exception processing, insight, and creativity. Whereas machines are strong at collecting things, storing things, doing routine processing, and transmitting things. At the dawn of the Industrial Revolution, thinkers like economist Adam Smith wondered what would happen to the workforce as owners deployed additional machines to automate the work which people had previously done. Would labor's share of the output made by the companies go way down as machines took over their jobs? In fact, nothing like that happened despite the worries people have entertained in all the time since, at least to the current day. If we look at this chart, which plots the employee share of total income between 1850 and 1990 for two countries, the United Kingdom, that is Great Britain, and the United States, we see that income share to owners is not increasing as machines do more and more. In fact, as machines grew more important than natural resources like land as capital, labor share got much bigger, growing from about half of output to about 3/4 these days. As machines have been deployed in ever greater numbers in all sorts of economic activities, the mix of jobs that people do has changed dramatically. And it didn't wait until the advent of the computer to have this take place. We see here the distribution of jobs in three sectors: agriculture, industry, and services in the United States between 1840 and 1994. And you see back in 1840, more than 2/3 of the workforce was in agriculture. And that continuously plummeted as additional mechanization of agriculture took place until around 1970, when it couldn't go down anymore and was a negligible fraction of the entire workforce. Of course, some of the work we had called agriculture had gone to other places. On the dairy farm in Poland, on which my grandfather grew up, they had a solar-powered farm. Horses did the heavy plowing work, and they were powered by fodder grown right there on the premises. Of course, today, a farmer uses a tractor, and that tractor is not birthed on the farm, but comes from a tractor factory and is maintained by a mechanic and is powered by diesel fuel, which comes from petroleum in Alaska or Saudi Arabia or somewhere, which is refined in New Jersey before delivered to him. So the farm is no longer the standalone operation it once was. So in fact, the number of people involved in helping us grow our foods and other plant materials and animal produce is larger than the few percent you see here, but it is still a minority of the workforce. For a while, as farm jobs went down, both industry and service jobs went up and maintained about the same fraction of the workforce, growing to about 40% of it each around 1960. But then something amazing happened. The number of people required for industrial output dropped dramatically. And I think that's probably a reflection of all sorts of sophisticated machines that were introduced as electronics advanced and eventually blossomed into robots. And we see the biggest change, though, occurred in the decade of the 60s, when service jobs zoomed up and industrial jobs zoomed down. Industrial jobs are now less than 20% of the workforce, and service jobs constitute nearly 3 jobs out of 4. The growth of the creative class in America, 1900 to 1999. In this graphic, we see the analysis of economic development professor Richard Florida, which shows in detail the way the American workforce evolved in the course of the 20th century. And rather than simply talk about agricultural, service, and industrial jobs, he breaks down service jobs into 2 subcategories, or really 3. I will let you read the whole thing if you have an inclination to, but the point of his work is that for more and more jobs, the use of creativity that his original thinking is becoming more and more important, and that what he calls the creative occupations or the creative class now constitutes 30% of the jobs in America and takes home nearly half of the total payroll. Congratulations and thank you for your patience. You have now reached the end of this lesson introducing you to computers and information technology. At this point, I'm going to append a couple of pages of information which are perhaps useful to you. They come from material that I taught about a year ago at the library. The first of these you see on this page. It gives an outline of the joys and woes of using a personal computer. It reprises some of what we talked about during this lesson and adds some additional information. You're going to need to use a mouse or the page up and page down keys to look at this whole page because it exceeds the size of the little window in which it is put. Then, after you've studied that, you might move on to the next page, which gives you additional resources where you can learn more. Here, then, is the absolutely final page, a computer learning resource guide, which I prepared about a year ago and recently revised, and it points you to additional sources of information for learning about computers. Again, just like the previous page, you're going to need the mouse or the page up and page down keys on your keyboard to look at the entire thing. But I talk about books and videos you can loan from the library, courses taught at West Central Technical College in Waco here in Haralson County or at other campuses, syndicated TV programs you might like to look at. In our next lesson, we will learn how to use the World Wide Web, and there is an enormous amount of information on the web for you to refer to, which is why it becomes the first skill I want to, the first practical skill I want to teach you. And then additionally, we have some interactive compact discs or CDs. There's one in one of the machines here at the library which tries to help you learn a particular type of software called Windows XP, which is in current use. Anyway, thank you again for your patience, and I hope you will have the opportunity to attend some of the additional courses the Friends of the Library will present on computers and the internet during summer 2005. The librarian can help you by giving you a copy of the notes we've prepared for learning how to surf the internet's World Wide Web. They're very carefully written, and it will be of advantage to you to take a close look at them. So good luck, and do come back and learn some more with us. It's been fun trying to help you along your way. Bye-bye.